everyone, welcome. Thank you for joining us. My name is Jessica and I'm here with my colleagues Julia, Andrew, and Missy, and today we'll be presenting Bubble. Bubble is an automated open source solution for deploying dynamic front-end preview apps. We're going to start with a brief overview of the history of web development to provide some context around the type of apps Bubble supports. Then we'll get into the problem Bubble solves and an example of an organization that may encounter that problem before explaining further what preview apps are and taking a look at existing solutions within the preview app space. Next, we'll introduce you to the features Bubble offers and give a brief demo on how to use it, followed by a section on how we built Bubble, including the design decisions and trade-offs we made. Finally, we'll dive into challenges we encountered during implementation and how we'd like to expand and improve upon Bubble in the future. To understand Bubble's use case, we'll need to be familiar with the web development architecture a typical Bubble user's application would be built with. Let's take a step back and walk through a brief history of how web development approaches have evolved over time. The traditional approach for building web applications was based on a process called server-side rendering, or SSR. With SSR, when a client, for example a user's browser, requests a page from a website, the server is responsible for fetching any necessary data in regards to the specific request from the database, generating the HTML components with the retrieved data and assets, and then sending back the fully generated HTML files to the client so they can be displayed to the user. With every incoming request from the client, the server is kept busy repeating the heavy lifting of retrieving data and generating pages. As websites grew to serve more content, it became clear that some of it didn't necessarily need to be completely dynamic, meaning there would be little to no changes required for some pages on every request. For example, consider a company landing page or a blog post, where the content of these pages can largely stay the same regardless of who's requesting it. It would be inefficient to have the server dynamically generate these kinds of static pages each time a client makes a request. This led to the rise in popularity of static site generation, or SSG. With statically generated sites, HTML pages are pre-built before a user ever makes a request for them. At build time, a server is responsible for retrieving data and fully generating the HTML. This process is very similar to server-side rendering, but the key difference lies in when the server carries out this responsibility. With SSR, this happens at request time, but with SSG, the HTML is generated before it's ever requested. The pre-built HTML and other necessary assets are then cached in a CDN, a content delivery network. A CDN is a geographically distributed group of servers that can quickly deliver content from a location close to the client at request time. Now that we have an idea of how each approach works, we can take a look at what types of applications would be better served by each strategy. Both SSR and SSG are beneficial for apps that value search engine optimization, or SEO, as the HTML sent back to the client is fully formed for web crawlers to parse and index. From there, the use cases differ. Only server-side rendering makes it possible to dynamically retrieve data without needing to make a public API call using client-side JavaScript. This is necessary for apps that use secrets that shouldn't be publicly accessible. Server-side rendering is a good fit for apps whose page content needs to remain up to date, since the server regenerates the page on every single request. In contrast, static site generation isn't well suited for frequent changes, since a build and deployment process must be executed each time a page's content needs to be updated. Static site generation is particularly useful for sites that require fast page loads, since pages are very quickly served by a CDN. With server-side rendering, even though initial page loads are typically fast, there may be slower subsequent loading times. In addition, SSR can lead to servers being overloaded during periods of high traffic, since they always have to generate the HTML at request time. With SSG, there is no need for a server at request time since generating the HTML was done beforehand. Finally, SSG is a better fit for scaling for many users since CDNs by default can handle increased traffic at scale. An SSR architecture by nature does not have the same benefit. Historically, applications could be categorized into using either SSR or SSG. However, modern web development frameworks have recently begun to blur the lines between static and dynamic applications in order to bring about more flexibility and allow developers to fully optimize how a user interacts with an application. Some examples of popular frameworks which support a hybrid approach, combining both server-side rendering and static site generation, are Next.js, Gatsby, and Vue. For applications that are content-rich but only require frequent dynamic data retrieval for select pages, it makes sense to use static site generation to pre-build simpler static pages in order to be able to serve those up quickly, while employing server-side rendering for pages requiring frequently changes, up-to-date content on demand. A common real-world use case for this blended approach is with e-commerce applications. Let's consider a hypothetical company named Giraffe as an example to better illustrate Bubble's use case. Giraffe is an e-commerce application that sells giraffe-related merchandise. They self-host an online storefront implemented with the Next.js framework. Their application uses a mix of static site generation and server-side rendering to generate content. For example, the product categories page is generated through SSG, while product recommendation pages, which are unique to every user, are generated with SSR. Recently, Giraffe's been doing very well. They've hired additional engineers to develop new features and bring a new look to their website, but they're starting to experience bottlenecks during the development process. Since multiple developers often work on new features simultaneously and also need to collaborate with various other departments, collecting feedback from different teams is starting to take too long or lead to a lot of back and forth, even for very simple UI changes. At this point, Giraffe's wondering, what can they do to streamline this process? Prior to the recent expansions in their organization and additions to their site, sharing progress was easier for developers at Giraffe. They used manual approaches like sending screenshots to each other or screen sharing for interactive features. Occasionally, when non-technical stakeholders from other teams wanted to look at the progress more closely, developers would take the time to help them pull down the code and run it on their local machine. However, with larger teams, including remote colleagues and more non-technical stakeholders who need to approve changes, it's no longer practical to spend increasing amounts of developer time helping colleagues download and run local versions of the application to review changes. One tool that Giraffe uses as part of their development workflow is a shared staging environment. This is an environment shared amongst all developers collaborating on a repository. A shared staging environment aims to mimic the production environment as closely as possible to ensure all new changes are working as intended before they are released live. Different types of testing can occur when code is pushed to this kind of environment. For example, load testing to simulate real-life traffic and determine a website's performance under such conditions. Using a shared staging environment gives non-technical stakeholders a way to examine changes without having to build and run the application themselves, allowing them to examine in development UI and UX changes and give feedback so modifications can be made. However, having multiple teams adding different changes to a single environment presented another set of challenges to Giraffe's workflow. Since there is only one staging environment for Giraffe's developers to use, all newly developed features ended up living together, intermingled within a single environment. Batching together multiple distinct changes in this way caused bugs to arise that were difficult to troubleshoot because they could have stemmed from conflicts between any of the code updates pushed to the staging environment by different developers. This type of workflow also led to less frequent and more bloated releases. When there's one centralized environment for non-technical stakeholders to use, review tends to happen in larger batches. And when something went wrong and a release needed to be rolled back, it was much more challenging since the releases weren't atomic. In an attempt to resolve these issues, Giraffe switched to queuing instead, having only one development team at a time use the staging environment. This avoided the bugs, conflicts, and bloated releases that occurred when distinct changes were all batched together, but in turn has added a different set of problems to their development workflow. With only one team being allowed to use the shared environment at a time, developers now have to wait for the environment to be freed up before they can use it. One side effect of queuing is a higher risk of deploying unsafe code if a developer mistakenly rushes to deploy another colleague's work in an attempt to free up the staging environment for their own use. Another consequence of queuing has seen that valuable developer time is wasted. Long feedback loops have occurred since any previous changes need to be completed and moved out of the shared staging environment before the next in-line change can be reviewed. Now I'm going to hand it off to Missy, who will introduce us to what preview apps are and how they can reduce some of these issues Giraffe has encountered.
Thank you, Jess. Because of the challenges associated with using their shared staging environment to iterate on UI/UX changes, Giraffe is looking for other options that could allow them to shorten their feedback loop and reduce bugs. Preview apps are one way to allow non-technical stakeholders to look at UI/UX changes faster, so this feedback loop can be shortened. Let's take a look at preview apps in more detail. Preview apps are ephemeral, lightweight, and fully functional versions of an application that can be easily built and deployed, and just as easily torn down. With preview apps, multiple versions of a site can be quickly deployed in isolation, so non-technical stakeholders can more easily give feedback on UI/UX changes, and developers can more quickly iterate after receiving that feedback. Using preview apps, every time a new change is ready to be previewed, a Giraffe developer can deploy a new preview app and share its URL with all relevant stakeholders for evaluation. Here's an example of a development workflow using preview apps. When a developer is ready to share their new feature, they initiate a pull request for their feature branch. A preview app is automatically built and deployed with the new feature code, and a unique URL is generated to access each preview app. Product managers and non-technical teams interested in the feature use this URL for reviewing the changes. The developer makes any necessary code revisions based on resulting feedback and then commits to the same feature branch. A new preview app is deployed containing the new revisions, and it has its own distinct URL. The changes can be previewed once more, and different iterations of the feature can be compared side by side using their corresponding preview app URLs. This feedback loop using preview apps continues until all stakeholders are happy with the new feature, at which point the code can proceed to the next step in the development pipeline. Once the developer merges their feature branch, the pull request is closed, and any connected preview apps are automatically torn down. Preview apps help to reduce some of the headaches that occur when stakeholders use a shared staging environment to review and discuss UI/UX changes. Each new feature can be reviewed in isolation from other app changes that are still under development, eliminating the chances for hard-to-track down bugs that may crop up from code conflicts with other new features. In addition, since each developer can deploy and share a preview app for each new feature as frequently as they'd like, they can receive feedback from all stakeholders faster, leading to a more efficient development process with a shortened feedback loop. While preview apps help to streamline the process for developing front-end features, they may not be the right choice for everyone. Since they're intended for testing new features in isolation, preview apps aren't a good fit for testing how multiple changes would integrate with one another. They also incur costs, as additional infrastructure is provisioned for each preview deployment. And since each preview app has its own URL, interested parties need to manage multiple links, which could get unwieldy as more previews are deployed. Preview apps come with additional drawbacks, depending on whether a team chooses a third-party preview app service or decides to DIY their own. The former racks up more costs in the form of usage fees and requires that the code and data are shared externally with the preview app provider, which may be a concern for some organizations. The DIY solution adds labor and opportunity costs in the form of development time. As the landscape of web development has changed and the lines between SSR and SSG have become blurred, the requirements for preview apps have grown. If only SSG, static site generation, is used, all that a preview app would need is a CDN to deliver static assets. For only SSR, server-side rendering, an application would only require a server. However, to support applications which utilize SSR and SSG together in a hybrid approach, preview app architecture must include both an application server and a CDN, and this adds significant complexity. Since Giraffe's site uses both SSR and SSG, they'll need to find a preview app provider that can handle this complexity to allow them to benefit from fully functional preview apps. Let's explore the existing solutions for preview apps and see how they might impact the development workflow of a company like Giraffe. One option would be the DIY approach. Building their own system would allow Giraffe to customize things according to their exact needs, while maintaining full control of their code and preview app infrastructure. The downside is that it's a time-consuming and complex task to make all the necessary decisions and build out all the components necessary to implement fully functional preview apps. To construct their DIY solution, Giraffe would need to examine multiple sets of trade-offs to decide where and how to build and deploy their preview apps. With their design decisions made, they would then need to implement their system, which would include configuring, building, and deploying static assets, routing, and business logic, as well as writing code to automate this entire process and integrate it into their development workflow. Given the time and resources it would take to implement their own system, Giraffe might prefer to look at already made options. Preview app solutions typically fall into two categories: feature and service. Both offer a variety of features and provide dynamic front-end preview apps that support any combination of implementations, including SSR and SSG. The first category, preview apps as a feature, refers to preview app functionality that is included as part of a hosting platform. Preview apps as a feature are generally easy to set up and use, and offer an abundance of functionality. However, they require a company's code and data to be hosted and deployed using that provider's infrastructure. If a company is already using a platform like Vercel or Netlify, it would be simple for them to leverage the preview app features they already have access to. But changing hosting providers is a large and complex undertaking, and it typically doesn't make sense to do so for the sole purpose of using preview apps. The other category is preview apps as a service. These are standalone options, which can be used on their own without changing hosting platforms. As a separate service, these options require more setup time and configuration, often requiring the user to write custom files before preview apps can be built and deployed. These options are also typically subscription-based, requiring payment for the service regardless of how much or how little it is being used. Out of all the currently available preview app solutions, only one, GitLab, is open source, and it provides preview apps as a feature. So it means that code has to be hosted on its platform to access its preview app functionality. Now, Andrew is going to show us how our solution, Bubble, fits into the mix.
Thanks, Missy. Bubble provides another way for Giraffe to benefit from preview apps with a different set of trade-offs than existing solutions or implementing their own from scratch. Let's take a look at how Bubble compares to the solutions we've already discussed. Bubble combines some of the benefits of both preview apps as a feature and a DIY approach at the cost of supporting fewer features. The benefits of using Bubble are that a company like Giraffe can have preview app functionality that's easy to set up and use, like preview apps as a feature, while maintaining complete control of their own code and data, like a DIY approach. The trade-off is that Bubble won't be completely customized in the same way a made-from-scratch solution would be, nor does it support the range of languages and frameworks that a hosting platform would. Bubble has several important features. It automatically deploys preview apps when a pull request is opened, as well as when subsequent commits are made to a branch associated with the pull request. Each deployment generates a shareable URL that will be posted on GitHub as a pull request comment. When the branch is merged or the pull request is closed, all associated preview apps will automatically be torn down. Bubble also provides two user interfaces: a visual dashboard where the user can manage preview apps across all their local repositories, and a command line interface, or CLI, where the user can interact with the preview apps for one repository at a time from its directory. Let's take a look at a few of Bubble's features in action. In order to integrate Bubble with an application, the user will need an AWS account configured with the AWS CLI, a GitHub repository for an application built with Next.js, and a GitHub token providing access to their repos. The user will first execute Bubble init in the project directory, This command initializes all necessary local files, sets up authorization information that's needed to provision the AWS resources for preview apps, and creates a DynamoDB table to store preview app metadata. Once Bubble is initialized in the project repository and its files have been pushed to GitHub, opening a pull request on a new branch will automatically trigger the deployment of a preview app, whose unique URL will be added to GitHub. The developer can then share this link, and anyone can navigate through the fully functional app and preview the changes as needed. Additional commits to any branch with an open pull request will trigger deployment of another separate preview app with its own distinct URL. These preview apps will remain live until the pull request is merged or closed, or the user elects to manually destroy their preview apps. Users can deploy as many preview apps across as many branches as they need. Bubble also includes a dashboard, which provides preview app management across all Bubble integrated repositories. Through the dashboard, users are able to navigate to any of their preview apps, as well as the build logs for each deployment. The dashboard also provides an easy interface through which users can destroy all preview apps associated with a particular repository. Now, let's take a deeper look at how we built Bubble. Bubble consists of three main pieces of architecture: a local user interface, GitHub, and AWS. The first piece, the user interface, consists of two parts located on the user's local machine. Once Bubble is globally installed as an NPM package, the user can then access the CLI to initialize an instance of Bubble in a repository directory. This adds necessary files to the local repo and updates files for the dashboard to use. The dashboard is a locally run web application that provides a user-friendly visual interface for viewing, managing, and destroying preview apps. It combines a backend to make API calls to AWS and a fronthead for the user to view in their browser. The second piece of our architecture uses GitHub. Bubble uses GitHub Actions to automate the build, deploy, and destroy process for preview apps. These actions execute workflow files added by Bubble, which are triggered through initial pull requests, subsequent commits on branches with existing pull requests, or HTTP requests to GitHub servers sent via the Bubble CLI. GitHub Actions run on their own servers, so GitHub takes care of spinning them up and down and executing the workflow code. The final piece of our architecture uses several AWS services in order to deploy the infrastructure for all preview apps. Each individual preview app consists of 3 AWS microservices. Server-side rendering logic and API routes are deployed to Lambda at Edge functions. S3 buckets store static assets such as images and pre-built files, and CloudFront serves both static and dynamic content by associating the functions and S3 buckets to each route of each preview app. All preview apps in a repository share 2 additional AWS services. The AWS commands executed by Bubble are carried out through IAM users endowed only with the permissions needed in order to create, manage, and destroy Bubble preview apps. And DynamoDB tables are provisioned to persist and store metadata related to users' preview apps so they can be easily managed and later torn down. Now that we have a high-level overview of the various pieces of our architecture, let's zoom in further on the GitHub and AWS components to examine some of the trade-offs and design decisions we made in regards to where and how to build and deploy our preview apps. The first major design decision we tackled was where the build process should take place. Bubble automatically builds preview apps on 2 triggers. One is the opening of a new pull request, and the other is subsequent commits to a branch with an open pull request. Since these events occur within the context of a GitHub repository, we had to decide where we would be able to execute the build process as an automated response to these events. GitHub Actions proved to be well suited to our use case. It's an automation tool that allows users to execute code written in files called workflows using GitHub runners, which are temporary virtual servers that GitHub spins up and down. Here's how this process works. A Bubble workflow file in the user's repository is set to listen for pull requests. When a pull request is opened, the workflow is triggered, and GitHub automatically spins up a runner to execute that workflow, which then builds and deploys a preview app. After this process is complete, the GitHub runner is automatically spun down. Instead of having to provision and configure our own external build server to run each build process, which would add unnecessary complexity and setup work to our architecture, GitHub Actions provided a simpler way to integrate with GitHub and carry out the build process directly within the context of a repository. As with most engineering decisions, there are trade-offs associated with using GitHub Actions. One challenge with using GitHub runners is that they are entirely managed by GitHub and thus cannot be accessed directly, making it difficult to extract outputs and other environmental artifacts. In addition, development is much more constrained than it would be if we were configuring our own build server, since workflows can only be defined with YAML files. However, the benefits of using GitHub Actions ultimately outweighed these drawbacks when it came to Bubble's needs. GitHub Actions includes a free tier that we estimate provides enough compute to make building and deploying preview apps very inexpensive, if not free, for a typical mid-sized team using Bubble. Relying on GitHub runners is also much simpler than implementing and configuring our own build server, and so it abstracts complexity away from our architecture. Finally, since each section in a workflow file can be run on a separate GitHub runner, GitHub Actions allows Bubble to deploy and tear down preview apps in parallel, making this process more efficient. After determining where our builds would take place, we next had to determine how to build the preview apps and where to deploy them. Recall that the essential architectural component differentiating a static front-end application from a more complex dynamic one is the need for an application server to generate SSR pages at request time. Since Bubble aims to let users share new UI and UX features quickly and conveniently, we considered options that would allow us to build and deploy applications, including their own servers, in a lightweight and cost-efficient manner. One option would be to deploy the server-side logic and static assets together in a container. A container encapsulates both the application code and all runtime elements necessary to execute it together in one package. With containers, we wouldn't need to set up and configure multiple nodes of infrastructure or implement routing logic to connect them. Instead, we'd be able to deploy only one single entity for each preview app, as the entire application could be spun up in the container as a whole. Since there's only one piece to consider, containers can easily be moved around and deployed. However, containers are constantly running and would therefore incur cost even when no one is using the application. They also have longer build times since the virtualized OS and runtime need to be built and packaged together on top of the preview app itself. An alternative to containers would be deploying the server-side logic and static assets to separate services. Given our use case of providing temporary preview apps, we found serverless functions to be the most compelling option for deploying server-side logic. Despite being called serverless, these functions do actually run on servers, but they abstract away the logistics of provisioning server resources. There are no ongoing expenses. Developers are only charged for the server capacity that their application uses during the time it's actually being executed. Since they don't need to include system dependencies, serverless functions are also very fast to deploy, typically going live within milliseconds. One downside for serverless functions is the added complexity of the architecture for preview apps. As opposed to containers, using serverless functions requires multiple nodes of infrastructure as well as routing logic to direct traffic between them. Another inherent drawback is what's called cold starts. Since serverless functions aren't constantly running, they have to be spun up before beginning execution. This can sometimes take several seconds, which can lead to longer loading times for server-side rendered pages. Ultimately, we chose to use serverless functions rather than containers. Bubble's preview apps do not need to be highly performant, so cold starts are acceptable. In terms of the architectural complexity, although serverless functions necessitate additional infrastructure, being able to use separate services for SSR and SSG allows us to fully optimize for this hybrid approach. As we delved further into utilizing serverless functions for our preview apps, we considered 3 open source frameworks to help automate deployment. Now our teammate Julia will dive more into these options, as well as some challenges we encountered during implementation.
Thank you, Andrew. Terraform is the first tool we considered. Terraform is an infrastructure as code framework used to manage the lifecycle of cloud components. There are many existing modules of Terraform for deploying front-end applications that are free to utilize and actively maintained. Compared to other solutions, One of the most promising modules we found uses a more complex architecture to deploy apps. The AWS services used include CloudFront to handle incoming traffic, a Lambda at edge function that acts as a proxy handler to route requests, an S3 bucket for static content storage, Lambda functions for serving the dynamic SSR pages, and an API gateway that balances traffic between the Lambda functions. The cost of this heavy underlying infrastructure is lengthy deployment times. During our test runs using this module with multiple applications, we found that deploying one simple app would take more than 15 minutes. We also encountered a few deployment failures, which were challenging to debug because of this complexity, and ultimately led us to question the reliability of this option. Front-end Application Bundle, also called FAB, is another open source framework that enables users to deploy front-end applications through a CLI. FAB zips up the entire application and ships static assets and server-side logic separately. Thus, the user has the option to choose separate platforms for serving static and dynamic content. For example, they could deploy static assets to AWS S3 while deploying serverless functions with Cloudflare workers. Although it aims to be platform agnostic, for serverless functions, FAB is currently only streamlined for Cloudflare workers and AWS Lambdas. When using FAB to deploy a few test applications, it took no more than 5 minutes to deploy each app, which is significantly faster than other tools we considered, especially Terraform. However, unlike other options, FAB has not been maintained for more than a year and a half. The final option we considered was Serverless Framework. Serverless Framework deploys apps using only 3 AWS services: CloudFront, Lambda at Edge, and S3. This is a simpler architecture in comparison to the Terraform module, which may be a contributing factor to its faster deployment time. While provisioning the CloudFront distribution does take a few minutes, it still took less than half the time to deploy compared to Terraform. One downside of using Serverless Framework is that unlike the flexibility of FAB, it currently only supports deployment on AWS infrastructure. Moreover, server-side logic can only be deployed to Lambda at edge functions. However, while FAB is no longer actively maintained, Serverless Framework has continued to be a reliable framework, considering how many people use it. The maintainers are still active, and its latest version was released just a few months ago in March 2022. In the end, we decided to go with Serverless Framework to build and deploy Bubble's preview apps. Due to its reliability, relatively fast deployment time, and simplified architecture, which would best serve Bubble's goal of automating lightweight and convenient preview apps. Now that we've explored how Bubble works and some of the design decisions we made, let's dive further into 2 of the challenges we encountered during implementation. One of these challenges occurred when we were deleting preview apps. We decided to use the same mechanism to tear down preview apps through triggering Github Action workflow files. The workflows can be triggered automatically by the closing of a pull request or manually with the Bubble destroy CLI command. When the workflow to destroy a preview app is executed, all AWS resources provisioned for that preview app should be torn down. As we've mentioned, these resources include the S3 bucket storage, CloudFront distribution, and Lambda at edge functions. AWS associates Lambdas with the CloudFront distribution, so the order in which we delete each resource is important. In our Bubble destroy implementation, we first request that AWS remove S3 bucket storage, and then the CloudFront distribution, and finally the Lambdas. However, even when the CloudFront distributions are successfully deleted, issues often occur when we attempt to delete the Lambdas. They often require additional wait before they can be deleted. This amount of time can range anywhere from a few hours to a day. Upon further research, we learned this is an AWS limitation when working with Lambda at edge functions. So we had to find a solution to work around this issue. One solution we considered was polling, repeatedly trying to delete the Lambdas and checking whether or not the attempt was successful. This would involve setting up a process often referred to as a cron job, which enables developers to automatically and repeatedly execute scripts at specified times. With this approach, whenever the user executes the Bubble destroy command, Bubble would set up a cron job which would try deleting Lambdas periodically in the background until none remain. The downside to this approach is that cron jobs run on operating system, and thus will need to be configured differently depending on the user's OS. Multiple implementations would have to be developed for different systems, all of them including the cron job itself, as well as manually setting up logging in case of errors, monitoring these logs, and adding additional logic to restart a job if the computer is rebooted. Rather than relying on the user's local machine, another possibility would be implementing a cron job on AWS. However, this would increase costs for the user and become yet another cloud component to manage. We decided to take another approach for this specific task. Instead of cron jobs, we decided to add an additional command named bubble teardown, which users can run themselves sometime after running bubble destroy in order to remove any remaining lambda at edge functions. To make this change, we had to adjust how we maintain the information necessary to tell AWS to remove these functions. We decided to add an additional table to the DynamoDB database to store metadata for each lambda, which meant we also had to alter the workflow for building and deploying preview apps so that this lambda metadata was saved during each deployment. This new table is now used when the user runs bubble teardown, so that bubble can tell AWS which functions to delete. The table is then removed once all functions are successfully deleted. Modifying our build workflow and adding this additional table slightly increased the complexity of our application, but we felt it was simpler than implementing multiple cron jobs and the logic it would take to monitor and eventually remove them from the user system or AWS. Another challenge we experienced involved capturing the preview app's build logs and integrating them into our dashboard. Our initial plan was to capture and parse the logs so that we could include them in full on the dashboard, but this turned out to be surprisingly difficult to implement. As previously discussed, we use GitHub Actions to deploy and build preview apps, but a downside of using it is the opaque nature of its runtime environment. Our first attempts to capture the logs during the build process were unsuccessful because the action run logs are only available via an API call after the entire execution has finished. We ended up having to cache the run ID for each workflow on GitHub and then implement an entirely separate workflow, which was triggered immediately after each build action finished. This allowed us to access the build logs in their entirety within the new workflow. The next hurdle after retrieving the logs was cleaning and parsing them. As part of displaying workflow execution logs on their site, GitHub injects a variety of metadata and special character sequences. These sequences are useful for GitHub's web app, but they lead to numerous string parsing errors when handled within a workflow on a GitHub runner. Trying to parse these logs was a painstaking process of manually going through thousands of lines of logs and attempting to eliminate these inserted characters without removing meaningful log data. The number of edge cases that required special handling kept growing and growing with no end in sight. With increasing engineering complexity for this feature, in addition to the costs that would incur from storing the logs, we decided to reconsider this approach. Instead of processing the logs ourselves and making them available in full on the Bubble dashboard, we decided to add a link on the dashboard for each preview app's build log. When followed, this link takes the user directly to the GitHub workflow run, where they have the option to download the logs for that specific preview app. Although this option requires a couple more clicks for the user, it significantly reduces the complexity of Bubble itself, as well as the storage needs and costs of the user's AWS account. Now that we are well acquainted with Bubble and the design decisions that went into building it, we would like to briefly mention some features we want to include in the future. At the moment, Bubble only supports applications built with the Next.js framework. We would like to eventually add support for other front-end frameworks such as Gatsby and Vue. Our dashboard feature can only be viewed by the developer who installed Bubble. In the future, we would like the dashboard to be more distributed so that developers from the same team can share one dashboard to manage and view their preview apps in one place. Finally, Bubble's preview apps are currently only deployed on AWS infrastructure, but we would be interested in exploring how to integrate our solution with alternative cloud providers, such as Cloudflare and Google Cloud. Now, thank you for listening to our presentation. We will now open up for questions.
Okay, looks like we've got one. Carl says, awesome job. Looks like an amazing project. Thank you, Carl. Would love to hear more about the CLI feature. how did you approach this? For example, did you use a CLI framework like Oak Cliff? And what were the challenges around that task? I guess I'll go ahead and jump in and answer that one. So we did not use an Oak Cliff framework. I think one of the, or we didn't use any frameworks, including that one that I've not heard of, Carl. Some of the challenges were kind of bouncing back and forth between using GitHub Actions and just being able to program in JavaScript. So our command line interface is an NPM package. And for some of there's a collection of commands that we make available, and we kind of outline those a bit more in detail on our Bubble case study, which we'll make available at some point in the future. And so for some of the commands, we were able to kind of just write out the application logic in JavaScript, and we're able to use things like the AWS command line interface tool as well. And so we kind of had to just bounce back and forth between sometimes coding a bit more freely using JavaScript and sometimes needing to execute those workflow files that we mentioned via GitHub Actions. And in that case, the environment's a little bit trickier to deal with since, like we said, we kind of have to use those constraints that GitHub enforces. Not sure if any of my other teammates have anything to add to that question specifically before we move on to the next one.
Yeah, no, I'd echo that, Missy. I think too, we also like talked a bit about just what commands, like in general, we should implement when setting up the CLI and how we could kind of just let the user do everything they would need to do in regards to preview apps directly from the command line, but try to like make that process as easy as possible for them and automate that. So we did have to kind of consider how to save down like the GitHub access token and like the AWS credentials and everything, and where to store those, whether locally or in like the GitHub secrets, in order to be able to kind of automate that whole process. So I think that was a bit challenging as well, in addition to working with the workflows like Missy mentioned.
Mm-hmm. Oh yeah, we definitely had a lot of conversations around basically where we were going to store all that sensitive information that we need to basically do anything in AWS on behalf of the user. So that was kind of actually one of the conversations we spent, I'd say, longer amount of time on. Okay, Audrey's wondering, what part of building Bubble did you find the most interesting or exciting?
Maybe I will jump in on that one. I guess together with Juan's question as well, it might be a very similar answer. I think there's two parts I found exciting, interesting to do. One was finding the open source, looking at other open source projects that were deploying Next.js framework applications specifically. I think partially is to look at the trade-offs between those projects and at how other people approached it, and if it was a good use case for our project. It partially verified our thesis on why people actually needed or would use our open source project. And partially, it was also a very agonizing process of trying out all of these different frameworks, and each one took a very long time. Some of them took a very long time to deploy and didn't even work at the end, and trying to figure out why it didn't work and perhaps what we could learn from all those failures ourselves. I think second part that was interesting to do was when we implemented the dashboard. We were initially very ambitious about all those things we could add to the dashboard, and maybe even have our own database for the dashboard. But one thing we learned from that when we discussed with our mentor was maybe stop making assumptions on what the user might need, because all of these, we were assuming, oh, they might need this, they might need that. But at the end of the day, maybe we were just adding additional work for ourselves without actually verifying it, would that be a useful feature? So that process was very interesting to me as well.
Totally agree. I'd say one of the most interesting parts for me too was just I think for all of us, this was the first time collaborating on a technical team. And so it felt really good once we got into a groove and kind of just knew what we had to do, knew who was doing what, and were able to like comfortably collaborate with each other. I found that super enjoyable.
Yeah, I would echo that. It was really nice to get experience on a larger scope of a project and practice working together and integrating different tools like staying synced up on Slack and using GitHub issues, all these kinds of things. I think the most exciting thing for me was probably seeing everything come together. And it kind of felt like one of those things where we just kept crunching along, and then all of a sudden things kind of seemed to almost everything just kind of came together, and that was really, really fun. It's also interesting talking about thinking of the complexity of just, even if one single piece is relatively simple to work with on its own, like putting together all these different things like a command line interface, or then working with GitHub or working with AWS or this other framework, it's interesting how much adding different pieces can really impact the complexity of your overall approach. That really struck me.
Yeah, I'd echo everything that y'all just said. I think like from a technical perspective, something like really specific was just working with GitHub Actions, like as tedious as it was to work with and to be able to like test out our project with it. That was really interesting to kind of learn how to work with. And then from like a non-technical perspective, just learning how to work with a team. I think Capstone like kind of helped prepare us because we had like the request bin project and like the React weeks could kind of like figure out how we work together as a group of 4 and then also like in pairs. And so we kind of like brought that over when we started working full time on our project. So it was kind of really nice learning how to kind of collaborate with one another, especially in different time zones and everything.
Yeah. Okay, so moving on, Audrey loves the giraffes. Thank you, Audrey. Arthur says, love the idea for a table for storing metadata. How did you arrive at that solution? Any future ideas for using that table for anything besides deleting lambdas? So who wants to think we can all like pounce on that question? But who wants to go for it?
We actually use 2 different tables, but mainly the tables are used for storing all the metadata related to each preview apps, so that when we actually deleting them, we have a mapping of where each resource is at, and then what's the ID for that resource. Future ideas for using that table. We initially, when we wanted to distribute the dashboard a bit more widely so that different users can potentially share the dashboard together, that might, if we decided to go down that route, we would have used table to store all kinds of user related data as well. Well, that came up a lot of different trade-offs too, because we weren't sure if the user would like that to begin with. Maybe they don't want to store their AWS or GitHub related keys in other people's database. But otherwise, that would be something to do in the future in terms of the tables.
Okay. Max is talking about the process. Max is asking about the process of deploying the serverless functions. How did you parse the Next.js files to determine what functions to deploy? So I can jump in on that one. Thankfully, we did not have to parse the Next.js files to determine which functions to deploy, because that's actually one of the amazing things about the serverless framework that we chose, is that it actually does go through and determine what needs to be, what's server-side logic and what can be served from the CDN. So that was kind of a big decision for us actually in whether we were going to go through and manually split up those two different types of logic ourselves and parse through and do that, or whether we could get a framework to do it for us. And so we were definitely hoping for the latter, just so that we wouldn't have to reinvent the wheel. And luckily, Serverless was able to help us with that. Next.js does, I believe, and either Jess or Andrew can jump in if I'm not doing this justice, but Next.js does, I believe, have a serverless mode that you can select to build. So it will actually like build out your files and more neatly sort of separate the server-side logic from the pages that would be statically generated. So if we did have to go through and parse them, I don't think it would have been too tricky, but it might have just added a bit more of a extra step there. Okay. What was the most challenging part of working with AWS?
Sorry, go ahead. Okay, just maybe a few points from me. I find one is I actually don't think their documentation is that great. Every time we were looking for answers, it seems to be answers are all over the place. You would imagine them at one web page, but that's not really the case. I think second part is also, even though it's such a large organization, you would assume their products are very complete, has less holes, but even like with that Lambda situation we encountered, we were really surprised about it because a lot of people had the same issues. And it seems like an obvious thing to fix, but they didn't really fix it. That was surprising.
Yeah, we were a bit surprised with that specific issue. I'd actually found at least a couple of instances where folks had to actually call an AWS representative on the phone to delete their Lambdas for them. So yeah, definitely that was a moment where we're like, really? AWS doesn't provide this service, or it doesn't work in this way that we're expecting it to. And if, of course we have, we don't know all the complexity that's lurking underneath, but it was a bit surprising. All right. Well, thank you so much, everyone, for coming and listening to our presentation, encouraging us and questioning us. It was a lot of fun creating it and presenting it to you all.